Okay, so let's see what are the most common techniques to prove this positive invariance that we talked about. So let's just assume that the existence is satisfied on the interval 0 infinity for the time t. So suppose that the solution is defined for all t greater than 0, and just we need to show that the solution stays positive if it starts positive. So one typical situation when that happens, and this happens so often in many models that the proof that I'm going to show you, it's not even mentioned. You just basically indicate or say that standard means can show that the solution is positive. So the situation is when in the differential equation, you can factor the dependent variable. So imagine that your dependent variable, the population, or whatever the dependent variable indicates, big X of t, I'm sorry, X of t, is part of this type of ODE in which X is a factor on the right side. We can show that if the initial condition, the initial value is positive, then X of t is also positive. And so this situation actually appears often, like I said, in many models, including the epidemic models. So for example, the equation for the infected class typically has this property. Often the infected class, not always, but often it contains terms that have I as a factor. So for one thing, you could have the new source of infection, the infection rate. Let's say you have some natural mortality, maybe you have some recovery. All of these appear typically as per capita rates for the infected class. So overall, you would notice that you can factor I, and then you have just a bunch of other stuff in parentheses. So as I said before, if the existence of solution is ensured, this feature of being able to pull out the dependent variable on the right-hand side is enough basically to conclude that if initial condition is positive, then the solution stays positive as well. So the way to see why that happens is to make some sort of separation of variables. We don't really solve for X of t, but we rewrite the ODE in a different form. So if we divide both sides by x, so on the left side we have x prime over x equals f of t, x of t, and let's just integrate both sides between 0 and t. Normally I'll have to change the variable from t to a dummy variable inside here, but I'm not going to bother for now too much. Let's just imagine that the right hand side, this integral of whatever you have here, is some function of t. It contains the undetermined function x of t, but let's imagine that we know this exists. So then one can look at the integral over the right hand side together, right? I mean, it would be the integral of something that contains t and maybe x of t, but overall we can think of that as a function of t. Now, because of this way I wrote this integral, notice that big F of 0 is 0, right? Because that will be just the integral from 0 to 0. We don't need to know what this function is. That's the whole point. And on the left side, we can write that antiderivative as natural log, because it's x prime over x, natural log of x of t between 0 and t. And on the right-hand side, big F of t. So if you plug in t and 0 and take the difference, then we can actually get x of t by itself. So on one hand, this is natural log of x of t over x naught, some function of t on the right hand side, and when we exponentiate both sides, we have x of t over x naught equals e to the f of t, and from here we can conclude that absolute value of x of t is absolute value of x naught e to the f of t. So basically, if your ODE, again, is shown that a solution exists and it's unique, there is something called uniqueness, and existence and uniqueness of solutions starting with an initial value. So if that is established, this extra factor of x, the fact that you have this extra factor, allows you to basically rewrite the equation in this form. This isn't the explicit solution. Remember, this big f of t is a big mess here, right? I mean, it's something that contains little x of t as well. So it's like the same equation in a different form. You can call this the integral form of the original ODE. But it serves the purpose of establishing the positivity, because now notice that if x naught is positive, then the left side must be positive as well, because remember, we have uniqueness of solutions. So normally, if you eliminate the absolute value, you would say that x of t is plus minus this right-hand side. So the two possibilities for x of t would be x naught e to the f of t, or the other one with a negative sign. However, because we started with the initial condition x naught, then we need, the uniqueness of solution forces us to conclude that this is the solution. This is the format of the solution if we start with a positive initial condition. So in other words, starting with a positive initial condition and the existence of this extra factor x allows us to conclude that we can rewrite x of t for all time t in the form of a positive constant, your positive initial condition, and some exponential. Now, no matter what big f of t is, we don't need to determine what it is. That exponential, of course, is positive, like any other exponential with base e. So we don't need to do this all over again. Each time in the model, when you can factor the dependent variable, then we can conclude that positive initial conditions implies the solution stays positive. There's another situation that appears quite often that I want to go through right now. And this one, actually, I'm going to illustrate it in a more intuitive format, so to speak. Let's say you have an ODE with lots of bunch of stuff on the right-hand side. If by replacing x with 0 on the right-hand side, x prime is strictly positive, then x of t remains bounded away from 0. So it remains positive, but in a sense, it's an even stronger positivity condition than the previous case, because not only remains positive, but actually it doesn't even come close to 0 in the limit sense. I should say it can come close to 0, but it still remains bounded away from 0. So there will be a certain neighborhood around 0 that x of t will not cross. And we're going to illustrate this with a very simple ODE. And I'm not going to make an official proof out of it, but with a very simple ODE, we can actually understand this quite easily. So suppose, for example, that the ODE I'm going to talk about is x prime equals 5 minus x. And x of 0, let's say, equals 2. This actually can be solved explicitly, and I'm going to do it. I'm not going to get into the way to solve it explicitly. It's the general solution is going to be some constant e to the minus t plus 5. Those of you who do differential equations know this, how to solve this quickly. I'm not going to get into the method right now. And the constant comes from the initial condition, so x of 0 equals 2, which means the constant in this case is minus 3. So the explicit solution for this initial value problem is 5 minus 3 e to the minus t. Okay, we don't need to find the explicit solution to prove that this solution actually stays positive. So the intuitive, imagine you don't know how to solve this. The intuitive approach that I mentioned in the previous page is that let's look what happens to x of t if x of t becomes very, very small. So suppose that if I sketch the solution, if I try to visualize what the solution does, I don't know what x of t does, right? I know that I start with some initial positive condition, and I have no idea what x of t does. But I want to know what happens if x of t ever comes close to being 0. So what happens if x of t at some point approaches 0, threatening, let's say, to go in the negative territory, which we don't want in a biological model? Well, we can estimate this situation by saying, well, if x really comes close to 0, then x prime of t really comes close to 5 minus 0, which is strictly positive. Now we know what happens if x prime is positive, right? I mean, if it's strictly positive, then x increases. So by the time it has any chance to get too close to 0, x of t will gonna be increasing. So I know for a fact that if I approach 0 close enough, so in other words, if x gets close enough to 0, the derivative becomes strictly positive, and then x of t might increase again. Will have to increase again. And again, remember, I don't know what x of t does. Maybe I don't have no idea. In this case, I do, of course. But let's suppose I have no idea. Maybe it goes up, it goes down. But I know for a fact that whenever it comes close to 0, that's going to increase again. So in that sense, we can conclude that x of t remains bounded away from 0, which is a stronger positivity conditions, if you want. So all you have to do is to replace x with 0 on the right-hand side and check to see if the derivative becomes strictly positive. So with these two techniques, we can actually validate pretty much all the models we're going to encounter. So let me give you briefly one quick example. So suppose, for instance, you have an epidemic model in which the susceptible class has a constant input of the population. Let's call it K. Then we have the infection rate, mortality rate, and then the infected class, lambda Si minus mu I, maybe some additional disease mortality, let's call it DI, and maybe some recovery. So let's put some transfer back from I to S. So once again, these are all biological constants, K greater than 0, mu, R, D, lambda, all of these are positive constants. The infected rate, the death rate, the recovery, and so on and so forth. So how would we validate the model? How would we know that if we start with positive initial conditions, then the solutions remain positive? So we can start with the first technique and notice that on the second equation, I can pull out I. I want to point out it won't help to pull out I in equation of S. You can look to see if you can pull out S in the equation of S or I in the equation of I, and so on and so forth. So the fact that I can pull out I, based on the discussion we had before, that means I of t remains positive if, again, the initial condition for I is positive. So now we know that I of t remains positive. Now I can look at S of t, S prime, and we say, well, we cannot pull out S, but what happens if S ever comes close to 0? So replace S with 0 in S prime. So that means S prime, if S close to 0, becomes close to K plus Ri. So all of these terms can be neglected, right? If S is very small, if it comes close to 0, the right-hand side of S prime becomes K plus Ri. Now we previously proved that I remains positive. K is a strictly positive constant, so S prime is strictly positive if S dares to come close to 0, right? Which means S of t is also positive. Again, it's more than that. It's bounded away from 0, and often in some more fancier proofs that we're not going to get into, that's actually needed. The fact that that S of t doesn't actually approach zero. I mean, doesn't approach zero in the limit. So that only remains positive, but it's bounded away from zero. So in this class, I will require just these two techniques to show the validation. And we're not going to do it too often, but I think it's important to be aware of the issue because models already have a bad reputation of not being too realistic. At the very least, they should be biologically feasible. Because if they're not, there is a problem with a model that you can just neglect. Now, before we close this part of the lecture, let me just give you a brief example of a model that sometimes is used under the excuse that we don't use it for too long, and so therefore it's still fine if we don't use it for the time range in which it becomes negative. And I actually disagree with that kind of strongly. This is the so-called harvesting model. So imagine a population of fish, for instance, or any animals that you would want to hunt or harvest, so to speak. So let's say, to make it as simple as possible, let's say that population evolves according to an exponential ODE. So without any intervention, you have just a happy population that grows exponentially to infinity, right? So P of t goes to infinity if r is greater than 0. But then you decide that per unit of time, you're going to cool the population. So you're going to basically harvest the population, and you indicate that by a constant. In other words, a specific number of individuals are removed from the population if h is greater than 0. I mean, that specific number is given by a constant greater than 0. So we know already how to do the phase analysis. And notice that in this case, the ODE has an equilibrium point, which is h over r. So if you do the phase line analysis, 0 is somewhere here, and the equilibrium h over r is over here. And this equilibrium is going to be unstable. If you start with a constant, a value, an initial value greater than h over r, so if you plug in something greater than h over r, the derivative is positive. So p increases to infinity. And if you start with something less than h over r, the derivative is negative. So they use this model and they say, well, this is useful because it tells me that if p naught is greater than h over r, then p of t still goes to infinity. So in other words, it tells me basically to monitor the population size. So monitor population size and adjust h, in other words, the harvesting amount, so that you won't cause population decline. So in other words, if h is small enough so that it's below, this quantity is below p naught, or the population is above my intended harvesting rate, I can ensure the population still goes to infinity. The problem is that if you start below h over r, it doesn't just go to 0, it goes to minus infinity. So in other words, it predicts negative population size, which doesn't make any sense. So you won't be able to actually harvest h individuals per unit of time as you approach 0. So at some point in time, the model simply doesn't make any sense. In fact, we can write down the full solution. Again, don't worry if you didn't take differential equations, don't worry too much how this is obtained. I just want to illustrate a little bit what I'm talking about here. The explicit solution of this equation is given by this, and if you sketch the full solution, again, if you start above that critical point h over r, the solution goes to infinity exponentially, but if you start below it, it doesn't just go to 0, it goes actually to minus infinity. So if this thing is negative, since r is positive, the overall limit goes to minus infinity. So it crosses in the negative territory, and it predicts basically the negative population. The only excuse is to say, I'm going to use the model on the time range where the population is positive, but it's still an incorrect model. And the mistake is the fact that it assumes the possibility of harvesting H individuals at any point in time. And obviously, if the population gets too low, it will be impossible to find those H individuals. So you won't basically be able to maintain that constant harvesting rate. I suppose this is a matter of personal opinion as well, because again, if the population is really, really large and H is really, really small, according to the population size, it could still be maybe a reasonable approximation. But fundamentally, it's still a model that predicts negative population, and that is incorrect. It's an easy model. That's the issue, right? That's why it's preferred, because it's very easy to solve. To make it more realistic, you'll have to basically make the harvesting rate dependent on the population, to include the assumption that you won't be able to harvest a constant amount. So that's it. That's all I have for the validation of the models. We'll move on to some other topics in the next part related to this week. Stay tuned.